All right, welcome back to another amazing YouTube lesson. Today we are using powers of 10 to estimate quantities. We are entering the amazing world of scientific notation. We are going to learn all about scientific notation, why we use it, what it represents, and if you've never seen scientific notation before, spoiler alert, there are exponents. And we are going to add, and we are going to subtract, and we are going to multiply, and we are going to divide. But first, we need to learn what scientific notation is. So we are going to learn, essentially, scientific notation is a way that you can estimate large and small quantities by using a power of 10. So today's lesson is fairly easy. We're just going to be properly rounding and then comparing based on our powers of 10. Tomorrow's lesson is going to get a little bit more challenging because we're going to have to read and write numbers in scientific notation. But don't worry, I got you. So make sure you have your books open. I'm on page 65 right now, but I'm flipping to 66 that quick, like a ninja. So again, what is scientific notation and why do we use it? Well, if you're going to be doing any sort of job in the real world, that has to do with very, very large or very, very small numbers, you're going to be using scientific notation to estimate. It's easier to work with, believe it or not, once you get the hang of it, and it just makes your calculations much simpler to do. Again, this is an estimation. If you want exact numbers, then obviously you're going to use exact numbers. But you don't want to sit there and have to, let's say you're doing, for whatever reason, you have a job where you have to calculate the population of the world. If you don't need an exact number of people in the world, and another spoiler alert, I know, 2 in 1 sitting, um, you're never going to be able to tell exactly how many people are in the world. But either way, you don't want to have to put numbers like this into machines over and over and over and over and over again. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different chances to make an error. So you estimate using accurate rounding, so that the numbers that you're working with are just easier to use. Same thing as for really, really small numbers. You're going to see some that are teeny, teeny, tiny. Scientists, things that are really small, astronomers, astronauts, when we're talking about things that are very, very far away, all of those numbers can be very large or very small. Photographers, when they're zooming in, those are small numbers or large numbers. So there are actually a lot more fields that deal with these large and small numbers than you originally would think. So just a little fun fact. So I'm going to go ahead and just jump right into the examples. You don't have handout notes today. Tomorrow you are going to get 2. Something exciting to look forward to. But for today, it's just mostly in the book. Like I said, it's more of a simple lesson. So we're essentially going to be looking at big numbers. I'm going to teach you how to make them simpler. And then we're going to be using those powers of 10 to compare them. So we're at the bottom of page 66. We're just going to follow the directions for now and see where that gets us. Okay. So light travels 299,792,458 meters per second. That's a mouthful. Sound travels at 332 meters per second. So we want to use a power of 10 to compare the speed of light to the speed of sound. Obviously, if you're looking at these two numbers, one of them is significantly larger than the other. But that's not the point. The point right now is to learn how to work with these numbers. So the very first step that you're going to do is you're going to go ahead and you're going to round to the greatest place value. The greatest place value is going to be the 2 here in the 100 millions place. Now, for those of you that don't remember, if it's 4 or less, let it rest, leave it alone. If it's 5 or more, add 1 more. It is always the number behind that tells you what to do. So because there is a 9 here, it tells us to go ahead and add one more. Everything behind it now turns into a 0. Yep, 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 yep. If you're not making sounds while you're doing this, something is wrong. So 2 plus 1 is 3. And we have 1, 2, 3, 4, 5, 6, 7, 8 zeros. 3, 4, 5, 6, 7, 8. I shall not be limited to a box. I won't do it. So we rounded that to 300 million. How many zeros do we have in the rounded number? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 zeros. That is going to become our exponent. So we're going to keep the 3 and we're going to put the 8 as our exponent. And this is how you write the number in scientific notation, 3 times 10 to the 8. So whatever number that is not 0 gets to stay, and then the number of zeros turns into your exponent, because remember, each 0 represents one place value. Ones, tens, hundreds, thousands, 10,000, 100,000, million, 10 million. That's not a 0, but it would be your 100 million place value. So each 0 represents a different place value. You should know by now that we need to multiply by 10 to move from one place value to another, which is why we can get away with turning each of these zeros into an exponent. Okay? So we're going to do the same thing, but now we're going to do it with, what is this one? Sound. Okay. What is 322 rounded to the greatest place value? Well, the greatest place value we have here is the hundreds. We're going to go look at the tens to tell us what to do. 4 or less, let it rest. Means we do nothing. These become zeros. 3 plus nothing is just 3. Rounded it to 300. I'll stay in your box this time. Don't let it happen again. How many zeros do we have? 2 zeros. Remember, that becomes your exponent. And then the 3 gets to stay as it is. So that is 300 in scientific notation, 3 times 10 to the second power. 2 place values and a 3. Guess what 10 times 10 is? 100. I know there are other shows out there where people call out, but I'm really stuck on Dora. I can't remember. Her cousin's name I know is Diego, but I don't feel like that's the name of his show. Go Diego Go, maybe? Gosh, my kids are old. Anywho's. So 10 times 10 is 100, and 3 times 10 is 300. So the math works. I just didn't want to make you 10 times itself 8 times, but it would be 100 million. And then 3 times 100 million would be 300 million. So the math works. So now that we have our numbers, we have 3 times 10 to the 8th and 3 times 10 to the 2nd. You can see, obviously, 10 to the 8 is greater than 10 to the 2nd. We could see that immediately, but again, that's not the point. The point is, teaching you how to estimate using scientific notation. This is scientific notation. This is scientific notation. It's a whole number times a power of 10. We're going to get into that more tomorrow. All right. The convince me is a good one because these are big numbers that are a little bit easier to just see. So if you wanted to compare them, essentially you could just go, oh, 1, 1, 1, 2, this one's bigger. But if they wanted you to compare them in scientific notation, estimating, again, you would just round, count the zeros, and then you could go ahead and compare using those exponents. All right, let's go to 67. Oh my gosh. They're right here for us. Oh, here's a good example at the top of a really tiny, teeny, tiny number. Same rules apply, but here's what I'm going to tell you. And again, we'll get into this more tomorrow. Anytime you're dealing with a teeny, teeny, tiny number, you're going to know because it automatically starts with your decimal. So really, really big numbers, you'll notice. Let me see if I can't. Look at that. Boom. No decimal. Giant number. Teeny, teeny, tiny number, start with a decimal. If we were to round this or put this number in scientific notation, notice everything over here has positive exponents. Okay? Anytime you're dealing with teeny, teeny, tiny numbers, all of a sudden we switch to negative exponents. The number one mistake kiddos make here dealing with negatives is they forget that -4 is actually not greater than -3. Remember, negatives is owing people money. So it's better to owe people less. That's what we want. That's where our opening is going to go. All right. So decimals, teeny, teeny, tiny numbers get negative exponents. The negative exponents, the less you owe, the better it is. That's the one we want. That's the way we're going to open for. Those are your bigger numbers. All right, this one I think is positive, and that's really it for today. Ooh, we're going to do number 5 on the next page. Don't look. Don't spoil it. It's crazy. Don't look. Okay. So for example, 3, we're finding out how many times as much. So the same things for this one, this example they gave you. You're basically comparing them still. One moment, please. Try to cut that out. Okay, and we're back. There are approximately, that's a lot, 1 billion, 20 million cars in the world. The number of cars in the United States is approximately 239,800,000. So they want us to compare the number of cars in the world to that in the United States. So we're going to go ahead and estimate. So the first thing we're going to do is round to the greatest place value, which is this 1. The 0 tells us leave it alone. Everything else becomes, most of them were zeros. It's fine. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go ahead and shorthand it now. The 1 stays the same. So that's 1 times 10. And how many zeros did we write? 9. And this is in the world. Now we're going to do the US. Same thing. We're going to round here. The 3 tells us leave it alone. We're going to cross everything else out. They become zeros. 1, 2, 3, 4, 5, 6, 7, 8. The 2 gets to stay. And we wrote 8 zeros. So now we're going to compare them. Which is greater? The 2 may be greater, but this one has a whole other place value. It has 9 instead of 8. So this wins. This 9 trumps that 2. Okay, the exponent is always going to win over the single digit over here. So the world has more cars than the United States. Boop, boop. Times 10 to the 8. If they ask you about how many times greater, 9 minus 8 equals 1. 10 times 1 is 10. So there are about 10 times more in the world. Okay, so you just simply say, what's the difference, subtraction, between these two exponents, and then multiply that by 10. So there's about 10 times more in the world than there are in the US. All right, as promised, we're gonna go look at number 5 now. Oh, I'm so excited. Look at that number. That's a whole lot of loops and counting. Scientist records the mass of a proton as, can you tell I'm hungry? This, not gonna read it. Gram. use a single digit times a power of 10 to estimate the mass. So once again, we're going to get our rounding powers on. What is the largest digit here, my friends? It is not this one. It is this one. Remember, we're in decimal land, so everything is at the opposite end. So it's actually this 6 that's going to tell us what to do. 5 or more, we're going to add 1 more. And these actually just disappear. We don't need you anymore. Thanks for playing. Bye. But now we got to count all these zeros. And because it's a decimal and a teeny tiny number, we're going to have a negative exponent. So let's get to counting. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We have to stop behind the 1. So we know it's going to be times 10 to the negative 24, because that's how many zeros there were there. And then what's 1 plus 1? And that is how you write that in scientific notation. Single digit times a power of 10. The reason we can't stop on this side of our number is because that wouldn't be a single digit. It would still just be 0. So you always have to take it one more when you're dealing with the decimals so that you get that single digit, whatever it is, because it can't be 0. It has to be a natural number. That's right. Pulling out those 7th grade skills. Ugh, I love this one. You should go there one day. It's great. All right, that's it for today. I'm going to really stop the video this time. And I will see you guys tomorrow on the YouTube. Bye. Maybe.